Hello and welcome back. We are discussing section 2.5, marginal analysis and approximation using increments. We're going to tackle that second thing, approximate derivatives using increments and the differential. So approximation by increments is sort of a logical expansion of our marginal analysis thing. In fact, we could just call this marginal analysis with a change in x other than 1. So basically the only prerequisites here are that we have a function whose derivative exists at some point, and what we're trying to do is figure out what would happen near this function based just off of the derivative computation. So this is a little bit inscrutable here, but let's see if we can shed a little bit of light on it. So this says that f of some number, we'll break this down a little bit, is about the same as f at this starting value plus the derivative times some small change in x. So let's see if we can break this up a little bit. So this a thing is supposed to be our starting input. So it's just the input that we're kind of basing all of this off of. So we'll start with that. Delta x is supposed to represent a change in our x values. So this could be something, it should be small relative to a, basically. That's a hard thing to put mathematically, but if a was 100, then delta x could be 1 or 2 or some other tiny decimal, and that would give us probably a pretty good description. So, but like the delta means in a slope calculation, this is our change in input. So this is how much we're allowing our x values to vary from this starting input value. Okay, so this entire input says you're taking some value and then going up or down by some amount. So f of this would be the actual output at this point. And we're saying it's only approximately equal to what we're about to come up with. So delta x makes another appearance over here. But what I want to say about this right side is here's our starting output. So a was our starting input, so this is our starting output. And that's what we're basing all this stuff off of. So fine, here's our output. And then we're supposed to go up or down by some amount depending on whether the derivative is positive, for instance, or whether our change in values for x are positive or negative. Because in theory, we could go up or down by, we could go up by a negative amount, which is the same as going down. Okay, so basically what I'm supposed to imagine is that the thing we were doing with marginal analysis before amounts to this entire thing but without the delta x in there. Instead, delta x is the number 1. And that's because all we really did was use the derivative as a prediction of slope. And that's what the derivative does a good job of. We use the derivative as a prediction of slope for 1 unit change in x. So we only went up 1 in our previous examples with marginal analysis. This is supposed to allow us to change any amount in a particular direction. So what we did with marginal analysis before was we used the derivative to make this prediction of how much you would go up when x increases by 1. So this whole piece without delta x's in it is exactly the same as what we were doing in the last video. Okay, so as usual, this isn't going to make any sense till we try it out, and maybe not even then, we'll see. But just for terminology's sake, this delta x thing is sometimes called the differential of x, just how much it increases by. Okay, so a quick example to get us in the neighborhood here. So we'll pick a simple function, x cubed, and the idea is if we look at values that are close together, for instance, we could get an idea of what's going on at 4.02 if we look at the value of 4 first. I guess I should say, before we get too far into this is, even by normal standards, this is a pretty contrived example because there's nothing preventing us from just taking 4.02 and cubing it and getting our answer. The kind of thing I should be thinking about is, I wouldn't do it for x cubed, but if we were, for instance, making predictions about stock market trends, so if I wanted to look at market value of something being traded, the best I could do would be to come up with a formula that describes what has happened in the past, because I really don't know what's going to happen in the future. So if I have a formula that works up until, say now, it's 4 p.m. or something like that, and I'd like to know what's going to happen in the next few minutes, I don't really have a formula that accurately predicts that, but I do have the rate of change right now. I have some formula that works at the moment, and I can figure out the derivative right now. So if I use that starting value, for instance, the market value at the moment, that would be f of 4, and add on the derivative times the small change in time that I really like to look at, then I can figure out what the prediction would be, say, a couple of minutes from now, whatever 0.02 of an hour would be. So that's just some context you might be able to put behind this to put what we're doing in perspective. So this is what the approximation by increments tells me. If I want 4.02, then I could start at 4, since that's a value I know. I could look at the derivative at 4, and then delta x would be 0.02. That's the difference between 4 and 4.02. So this is the change in my input value. Well, I can go to f and ask, what do you look like at 4? So 4 cubed. The derivative of this thing would be 3x squared. So I could just write f of x in general would be 3x squared. But we wanted this evaluated at 4, so in goes 4 for the x's. But you'll notice that all this stuff is actually real numbers now. So we could just get 64.96 for our predicted output. Okay, so what that means is that we are guessing, this is still an approximation here, that our output would be 6.96. 64.96. We have the luxury in this particular example of knowing that we could have gone back to this original function and asked 4.02 and just verify that what we have is a decent approximation. There's some extra details here, but we're actually accurate out to the second decimal place. Let's try this for production function. So Kenzie is the owner of this yogurt stand. Here is her production expected. So if she puts in K capital per time period, I think it's every month, but she puts in K dollars in capital, then her production level is whatever 180 times that capital to the 1/3 power looks like. So we have an idea of what's currently going on, $500 spent on capital. And then the thing we're actually in charge of figuring out is approximate this increase if she invests an additional $50 in capital. So this approximate the change in something is kind of an indication that what we're looking for is this marginal analysis or this approximation by increments idea. I'll try to use one or the other of those phrases, marginal analysis or approximation by increments, whenever I really want you to use one of those things to make predictions. Sometimes we'll get forced into it because we don't have enough information beyond that, but at any rate. Okay, so we're trying to figure out what happens to production if capital goes up by 50. So our estimate is this, according to approximation by increments. We're using Q for our production function, which is kind of customary for this Cobb-Douglas production function, this thing we were given for Kenzie's yogurt stand. But so instead of F's, we've got Q's, and instead of X's, we've got K's, because there's capital for you. But other than that, this is just that formula back again. So just to double check the unit situation here, A is in hundreds of, K is in hundreds. So when we pick our starting value, 500 is our initial, and we would like to change by half of 100, by $50 in capital. So our delta K is 0.5 because again, our X's our inputs are in hundreds of dollars. So just rewriting this expression up here with those specifics, A is 5, delta K is 0.5, and here's our derivative. Everything else is plugged in. So A5, delta K, 0.5. So the right side is what we're working with here. We'd like to figure out the current level of capital, the current production value at a level of capital 5, how that production is changing at that level of capital, and then multiply by half a unit because we're not going a full unit up. All right, so just grabbing our derivative function. So we use power rule for Q. So the 1/3 power came down here, and then we decreased the exponent by 1. So this piece up here is the 1/3 that used to be there minus 1 due to power rule. All right, 180 times the third, though, is 60. So we have 60k to the negative 2/3 for our derivative function. That's really the only computation that we have to do as an aside to this value up top. So what we're getting is an approximation for a Q of 5.5. That's 185 to the 1/3. This is, again, just going back to Q. So this is not the derivative right there. This is actually using our derivative computation that we just managed up above. So there's Q prime. And then here's our delta K, change in capital. That's the best triangle ever. Okay, but with a little bit of computation, there's our output. So this is, again, a prediction for what production would look like increasing by $50 worth of capital. So new predicted level, I'm trying to use the word predicted because this derivative kind of computation is only guessing at what this would look like. Remember that the graph that has the tangent lines that show a tangent line close to the graph itself, but not exactly on it. So compared to Q of 5, her production level was 307.796. This was in gallons of yogurt, I think. So that predicted increase, 318 that we just got, minus the value that we started at, would be 10.259. Also, if you notice, really all we would have to do for that value is look at this derivative times delta k piece. That would tell us the predicted increase or decrease in value. So this number right here, I don't have it computed in front of us, but it should be 10.259. Okay, so that's our second video. We've accomplished approximation by increments. So we're going to tackle the final section in Chapter 2 when we come back.